Have you ever wondered whether the universe is real or merely convincing? Not an illusion, not a dream, but a reality generated by rules we cannot see. It is an idea that has escaped philosophy and entered popular culture. The simulation hypothesis. At first, it sounds like science fiction, a cosmic computer, artificial worlds, invisible programmers. Yet beneath the speculation lies a serious scientific question, not whether someone built our universe, but whether the structure of reality resembles computation more than we once imagined. Physics does not begin by asking who created the universe. It asks something more precise. How does reality behave? And if the universe follows consistent mathematical rules, could those rules, in principle, be implemented as a simulation? That possibility feels unsettling because it quietly challenges another assumption, that reality must be fundamentally different from a model of reality. We tend to imagine a sharp boundary between the real world and a computer simulation. One is physical, the other is artificial. One exists, the other imitates existence. But modern physics has repeatedly shown that intuition is not always a reliable guide. Light behaves as both wave and particle. Space and time depend on motion. Matter emerges from quantum fields. Information appears alongside energy and space-time as one of the central concepts of fundamental physics. Again and again, reality has become less intuitive, not less real, just stranger than expected. So before asking whether we live inside a simulation, we should ask a deeper question. What would physics actually require for such an idea to make sense? And just as importantly, what evidence would distinguish a simulated universe from an ordinary one? The answer is far less obvious than popular discussions usually suggest, because physics is not interested in imaginative possibilities alone. It is interested in explanations that make testable predictions. Without that, an idea may be intellectually stimulating, but it remains outside established science. Still, the simulation hypothesis persists, not because physicists have discovered hidden computer code, but because certain developments in information theory, quantum mechanics, and cosmology have encouraged people to think differently about what reality is made of. That shift deserves careful examination, not because it proves anything, but because it reveals something surprising about the nature of physical law itself. To understand why the simulation hypothesis attracts attention, begin with something familiar. Every computer simulation follows rules. Objects move according to algorithms. Time advances through calculations. Information changes from one state to another. Now compare that with physics. Particles evolve according to mathematical equations. Fields interact through precise symmetries. Energy is conserved. Information follows strict physical limits. The resemblance is undeniable. Both systems are governed by consistent rules. But resemblance is not identity. The laws of physics describe how nature behaves. They do not automatically imply that nature is being computed. Still, several observations invite comparison. Quantum mechanics tells us that physical systems contain finite amounts of information. Black hole thermodynamics suggests that information associated with a region of space scales with its surface area rather than its volume. This surprising relationship appears in the holographic principle. In certain theoretical frameworks, the information needed to describe a region of space can be represented on its boundary. That idea has profound mathematical importance. Yet, it does not literally imply that the universe is a computer screen. It simply reveals that space-time and information may be connected more deeply than classical intuition suggests. Another point often raised involves quantum uncertainty. Some have argued that reality appears detailed only when measured, much like a video game, rendering only the region visible to the player. The analogy sounds persuasive, but the physics says something different. Quantum systems are described by wave functions evolving continuously according to precise mathematical laws. Measurements reveal particular outcomes through physical interaction. Nothing in quantum mechanics requires reality to conserve computational resources in the way software does. The comparison is metaphorical, not experimental evidence. Likewise, the apparent discreteness of certain physical quantities does not imply digital computation. Energy levels in atoms are quantized. Angular momentum is quantized. Electric charge comes in discrete units. Yet space-time itself has not been experimentally shown to consist of discrete pixels. Some approaches to quantum gravity explore that possibility. Others remain entirely continuous. The evidence is still incomplete. Then, there is computation itself. The universe certainly performs physical processes that can be described computationally. Galaxies evolve, atoms interact, DNA stores information, brains process signals. But describing a system through computation does not mean the system is literally executing software written by an external intelligence. The distinction matters. Maps describe landscapes. They are not the landscapes themselves. Mathematics describes planetary motion. Planets do not orbit because equations force them to. The equations capture regularities already present. Physics consistently distinguishes description from mechanism, and that distinction becomes essential here. The strongest philosophical version of the simulation hypothesis was proposed by philosopher Nick Bostrom. His argument does not claim that simulations have been detected. Instead, it presents a logical trilemma. Perhaps civilizations never become technologically capable of simulating conscious beings. Perhaps they choose not to create such simulations. Or perhaps simulations become so numerous that, statistically, simulated observers vastly outnumber original ones. If the third possibility were true, then any randomly selected observer might be more likely to exist inside a simulation. Notice what this argument actually depends on, not physics. Probability. Assumptions about future civilizations. Assumptions about consciousness. Assumptions about computing power. Each assumption may be reasonable. Each may also be wrong. Physics neither confirms nor rejects them. Some researchers have proposed experimental tests. Could space-time exhibit tiny computational artifacts? Could ultra-high-energy cosmic rays reveal an underlying lattice? Could fundamental constants display numerical limitations consistent with finite computation? These ideas are intriguing. So far, none has produced convincing evidence. Every successful experiment continues to agree with established physical theories within observational limits. The universe behaves remarkably consistently. Whether that consistency reflects fundamental law or underlying computation remains unknown. Importantly, an ideal simulation designed to reproduce every observable consequence of physical law would be experimentally indistinguishable from an unsimulated universe. If every measurement yields identical results, physics cannot decide between the two. Science depends on observable differences. Without them, competing explanations remain interpretations rather than empirical discoveries. This reveals something subtle. The simulation hypothesis often appears to explain reality, yet, unless it predicts phenomena unavailable to ordinary physics, it explains no additional observations. It changes the story, not necessarily the science. There is another perspective worth considering. Modern physics increasingly describes reality through information, relationships, and mathematical structure. Quantum field theory replaces solid particles with excitations of fields. General relativity replaces gravitational force with space-time geometry. Quantum information emphasizes correlations rather than isolated objects. Reality already appears less material than classical intuition once suggested. But informational does not mean simulated. Mathematical does not mean artificial. Structured does not imply programmed. The universe may resemble computation because computation itself was developed by observing regularities already present in nature. Perhaps computers imitate physics, rather than physics imitating computers. The direction of resemblance is not obvious, and assuming one direction instead of the other quietly inserts conclusions that experiments have never established. So, can reality be simulated? Physics offers a careful answer. Perhaps. In principle, sufficiently advanced computation might reproduce many aspects of physical behavior. Whether consciousness itself could emerge within such a simulation remains an open, philosophical question. Whether an entire universe could be simulated depends on unknown limits involving computation, gravity, quantum information, and the nature of space-time. But a different question is often hidden beneath the first. Are we already inside such a simulation? Here, physics becomes much quieter. No accepted experiment demonstrates that we are. No established theory requires it. No observation currently distinguishes our universe from an underlying computational substrate. The hypothesis remains logically possible. It is not scientifically established, and that distinction matters. Because uncertainty is not evidence. Possibility is not confirmation. The absence of disproof is not proof. Science advances by narrowing possibilities through observation, not by choosing the most imaginative explanation. Yet, the simulation hypothesis performs an unexpected service. It forces us to ask what reality actually is. Is matter fundamental, or fields, or information? Are physical laws descriptions of deeper structure, or the deeper structure itself? Those questions remain active areas of research. Their answers may reshape physics regardless of whether simulations ever enter the picture. Perhaps the greatest lesson is not about computers at all. It is about assumptions. For centuries, we believed reality had to be solid. Then, fields replaced particles as the deeper description. We believed time flowed absolutely. Relativity challenged that certainty. We believed observation merely revealed an already complete world. Quantum mechanics revealed a more subtle relationship between systems and measurement. Each step forced us to separate intuition from evidence. The simulation hypothesis belongs to that tradition only if it accepts the same discipline. Ideas become science only when reality has the opportunity to disagree. Until then, they remain possibilities. Interesting, provocative, incomplete. Whether the universe is ultimately computational, mathematical, informational, or something beyond all current categories, one fact remains unchanged. Every experiment has revealed a universe astonishingly consistent with its own laws. Those laws continue to predict phenomena with extraordinary precision. And perhaps that is the deeper mystery, not whether reality resembles a simulation, but why reality, whatever its ultimate nature may be, is comprehensible at all. The more carefully we study the universe, the less it resembles our intuition, and the more it invites a question that reaches beyond every answer we have found so far. If reality follows such elegant rules, what is it that those rules are truly describing?